So as I mentioned before, uh, in the schedule that I attached in the Moodle system, there is a quiz, right? Today. No, no. Should be today, but I rearranged the schedule. So maybe it will be around during this, between this October. So maybe 13 or 15, right? Tuesday or Thursday. It will be 30 minutes quiz. So we will have um, our calculus class first, or maybe just the quiz first. Okay. The first 30 minutes for the class will be quiz, and then we can continue to um, our class. Okay. So this for the quiz. The quiz, okay, it's for chapter 1 and chapter 2. Okay. Okay, I need to explain to you, okay, because I think before I attach um, I attach to your Moodle system PDF files. The name of the file is chapter 1 and chapter 2. Okay. These files that I already attached in the Moodle, this is from 8th edition of calculus. It's a little bit different with our class. Okay. Yes, yes, the exercise one. So the exercise. So in the 8th edition, chapter 1 is functions and limit, and chapter 2 is derivative. Okay, but in 9th edition, this is what I intend to follow. Okay? This is the class. Okay? Our class follow this. Okay, our class following this. The difference in 9th edition, chapter 1 is only function. Chapter 2 is limit. And chapter 3 is derivative. Okay. So I already sent to you chapter 1 and 2, meaning the functions and limit only in chapter 1 in the PDF file. But if you have the book, then you can go to the chapter 1, chapter 2 in your book. Okay. The functions and limit. Okay. The details about the section, because there will be like 1, 1, 1, 2, right? 2, 1, 2, 2, right? Blah, 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 blah. The details I will announce later in the Moodle system. Okay, that's for quiz and information about the PDF files. Okay. Basically, the 8th edition and 9th edition, the content is the same. The difference is just the order. And the 9th edition may be having additional number problems in exercise. That's only the difference. But most of the chapters content all the same. Okay. Okay. So back to our class. Last time we have discussed this limits at infinity, right? There are one more sections in chapter 2. So this is still limit. Okay. It's called the intermediate value theorem. The same theorem also apply in polynomial. Okay. Similar theorem in polynomial, but this is to understand functions and limit. Okay. So I will draw a graph here, okay, to give a better illustration. Okay. I have 2 points, okay, A and f of A and B. Okay. In between this A and B, I can have any functions, continuous functions, any shape I want. Okay, let me just draw maybe, yeah, just a make up functions. So if this is a function here, wait, if this is a function, um, the functions continuous over A, B. Okay, the functions will take any value between f of A and f of B. Okay, so it means any uh, any value, let's say L, between f of A and f of B, there is C in the interval for which the f of C is L. Okay, so if you don't understand what it is, okay, just think of this graph. Okay, let's just say we have A, B as our interval. Okay, and we have maybe C is around here. C is here. And let me draw C up until here. And this is f of C, or this is L. Okay. So if your function is continuous, okay, over A and B, A and B is your interval, there will be a number C in which if you plug in C into the functions, okay, you will have the value of that function, f of C, is between FA and FB. Okay. It's it's not too, I think it's not too difficult to understand from the graph. Okay. So whenever you have C at the middle of A and B, anywhere, any point in between A and B, you will have f of C in between of FA and FB. Okay. So this means you can at least can proving that there is C, okay? And you can maybe determine what is the C if you know the value of the function. Okay? I think that's not too difficult, I think. One example to utilize this intermediate value theorem is if you have any polynomial function and you want to prove there is at least one root at the that makes the function zero. Okay, that root makes function zero. So you can also utilize the same method. Okay. For example, if I draw this graph, okay, if you have, okay, this is your A here, and this is your B. This is the interval here, A and B. This is the interval. No matter the functions look like, no matter how the function will shape will be shaping. Okay, it can be like this, right? Or any way you want, right? If you want to prove at least one root, you have this is negative, right? This is positive, the y-axis value, right? So the function need to crossing 0, right? Need to crossing the y-axis, right? The x-axis needs to crossing this. So if you have c here, f of c is obviously 0, right? So if you can prove that there is opposite signs in the end of each interval, then you have proven that there will be at least one root. Okay? That is one example for the intermediate value theorem. Let me give you one case, okay, study case. Okay. This is your function. It just start with the not too difficult functions. This is your functions, and this is your interval. Okay. And then how to prove? Okay, prove there is at least one root through intermediate, or I'll just write intermediate value theorem. So I think this function is easy to factorize, and you know the root directly, right? But according to the theorem, if you want to follow the theorem, then you need to prove f of a. In this case, the a is 3, b is 5. Let's just say f of 3. So 3 squared, right? Negative 3, negative 12. So 9 minus 3 is 6, minus 12 is negative 6. So a is around here. F5. So it will be 8, right? Positive 8. So this part is negative, this part is positive. So of course, from our previously discussed theorem, if you have A here and maybe B is around here, so the function should be crossing the x-axis, right? Which means because of the opposite signs, there is at least C in which f of C, and if you want to proving furthermore, you can proving that this is, you can factor that your x is actually 4. Okay, just easy example, and you can try to find another case and problem in the exercises. But this is to show that there are several types of problems using the intermediate value theorem. And also, the questions is similar to, like this. You have the interval, you have the functions, but maybe the function will be more complicated. This is just an easy example. Okay. Okay, I think it's easy to understand the theorem, right? Okay. I will start with the just reviewing our limit concept. Okay, evaluate limit. Okay, try these two questions. Raise your hand if you solve the questions. Maybe I give you 2-3 minutes to solve. Maybe 3 minutes to solve. Okay, for online students, don't worry about the quiz. I will announce later how we will proceed with the quiz for the online students. And no need for calculators, I think. If you finish, raise your hand. Yeah, I want to see your calculation. Finish? Oh, anyone finish? You finish? No? Okay, who finished? Finish? Finish? No? The clue for the second question is okay. Okay, so the first problem, um, remember every limit, okay? You need to test the limit first. Okay? You plug in the limit here, here. Okay? See if it is getting the answer or getting the indeterminate form, the 0 over 0. So when you plug in 0, this is secant 0 is 1, right? 1 over cos 0 is 1, right? So it should be 1, 1, it should be 1, right? The second question, I gave you the clue is, remember that limit as x approaches 0 for sine x over x is 1. This is from our previous proving. So let me write the step-by-step x cube and tangent cube here. Let me write the x cube, and the tangent I will use sine over cos to change the form. So cos will be here, and sine will be here. Okay. And then let me write the, this is still limit x0, and still limit x0 because, and then I will move the x cube here. Okay. Okay, I move x cube here. And then I will do a little bit algebra. So if you have sine 2x over 2x, this is also equaling 1. Okay. So if I have, let's make power of 3 here. So it will be, or I will directly make it 8x cubed. Okay. It's 1. Okay. So to make it only x cubed, I need to multiply by 8, right? So I will multiply, or I will change the this x cubed to, yeah, same, right? And then I will have limit x approaching 0, and 8, and inside I have, or I just write down the sine 2x over 2x and then cube. So x0 here, x0, this is 1, right? So this is 1 over 8. Okay, so in every trigonometric problems, okay, if you see any chances or possibility to have the sine x over x, you can make it into the form and make the limit as x approaching 0 of sine x over x, you can change to 1. Okay, so this is how to use the sine x over x, one example. Okay, any question before we continue to the next chapter? So after this section, we will go to the derivative. Okay, and I need your ID number later. Okay. Okay. Any questions? Any questions? Okay. Okay. I think the key point is to make this form. to make the sine x over x appear in your calculations. Okay, so we will going to the next section, which will be the derivatives. Okay, so of course, if you have 3x squared, if you have functions, of course now you're already familiar. If you have f prime x uh, or dy over dx, or I don't know in high school which one you are a lot of times used. Okay, but this is a few symbols that are been using in the derivatives usually. So the derivative, of course, 6x, right? I think you're already familiar with this, but let me give you the introduction. Okay, let me give you the introduction about the concept. Okay, so imagine you have a graph. Okay, okay, the graph is like that. This is f of x. Okay, okay. If I make the axis, the x-axis as time, and the y-axis as distance, it's similar to physics, right? The position, velocity, etc. in physics. Right? So if you have a graph, the functions, the blue line like this, okay. First, I want you to understand the graphs first. So imagine you are maybe moving or maybe running, right? So from zero, from starting point 0, you are moving along the time, and your distance is increasing, right? First it's here, and then increasing here, and then increasing here, maybe around here. So from the 0 point, from the starting position, you will see that you are getting faster, right? You're getting faster. The distance you traveled is longer, right? So this is getting faster. But after some point here, some point maybe around here, okay, your your distance is getting shorter, right? It's not as long as before, right? So this, from this interval, you're getting slower. I think if you try like running to check your stamina, sometimes you are running like in stable acceleration, right? You're running maybe around 5 times, 6 times, maybe after maybe 6 or 7, you will feel a little bit tired, right? And you are maybe getting slower, 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 and then eventually you get really, really tired and you cannot run anymore, right? So this is perfectly illustrates what running does. Okay? But the interesting here is what I want to show you, just as just an illustration to go to derivative. In every point here, there will be a change, right? Like the rate is changing. Okay, so the rate is changing. So every time we are talking about derivative, we are talking about the changing in rate. Okay, changing in rate. Either this is a distance traveled, right? Or maybe later in any case you can find, whenever you find derivative, there will be a changing. Sometimes something changed. But the interesting point is you are changing your tangent. Okay? So whenever your tangent line, this is tangent line, right? This is tangent. So whenever your tangent becoming more and more getting vertical, okay, you are getting increase in in this case speed, right? But whenever you are, let's change the color green. Whenever you are getting more and more towards horizontal, you are getting slower, right? Okay. In a sense, okay. And if you try to look up at any point here, if you try to to zoom in this point, what derivatives really mean at the very beginning, because we are relating tangent, right? The tangent is delta y and delta x, right? Y over x, the tangent, right? What derivatives really mean is when you are having limit as delta x approaching 0 of your delta, it will approach your, we say dy dx. Okay, this dy dx is what we call infinitely small changes. Okay, so when we see any derivatives, it is actually something really small that changed. Okay? In this case, in our mathematical world, it's y and x. Okay, there's a change in y and x in functions and its variable. Okay, that's the first case. And this infinitely small changes, okay, because your conditions, the first one is getting faster, the second one getting slower. So there is a change in your speed, right? But what derivatives really mean, because it's really, really small, the derivatives means in a sense of your speed, derivative mean, let me write here, instant, instant, you can say instant change, okay? Or in this case, it's instant velocity. What does it mean? So when you are running at one point, your velocity is maybe 5, maybe 6, maybe 7. That velocity, or we call instant velocity, is the derivative, okay? At exactly that moment. Okay? That derivative means, because if you see your speed is changing, right? But the derivative means the speed at one exact time. Okay, the velocity exact one time. Okay? Instant change. So that's the concept for just illustrations. Okay, just illustration. And next is I will dive into introduction with the formal definitions. Okay, so at least you now understand. And I think in physics also similar, right? With factor position, etc. Right? With t usually t squared plus blah 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 changing in t. Right? Okay, so a formal definition. Let me draw. Let's just say that it's the functions. Okay. Let me remind you the limit concept, and then we can go to derivative. If you have, this is A, this is B, this is f of A, this is f of B. Okay. Based on our understanding of tangent, or in this case, the second line here, line from P and Q. Okay. The gradient is delta y and delta x, right? So let's just write delta y over delta x. According to limit, okay, if we approach the delta x approaching 0, or in this case the b approaching a of our uh, tangent here, this is actually, we can say, when the point getting closer, closer, and closer, so you will see getting closer here, getting closer here. Okay. Eventually, it will approaching the A. We can also say this is our dy over dx. Or if you want to use the h definitions, this is x plus h. Okay. We can also write the limit as h approaching 0. This is the same meaning, okay? Same meaning, same usage, and this is h. This is dy over dx. This is f prime. And you have at least two forms in derivatives. So to make it from, for example, like I write before, from this function and going this 6x, actually the process is going inside this limit first, okay, before we are proving that we can do directly. So we are proving the 3x plus 8 squared minus 3x squared over 8. So we need to solve this first, and eventually it will get 6x. You need to expand this 2x 8 plus 8 squared minus 3x squared. It will getting that you can getting out the uh, 6x plus 6h, right? And this h, yeah. And plug in h to here, it will be 6x, right? So actually, this is the derivative, okay? The derivative at the early concept. Okay? To prove that when you derive the 3x squared becoming 6x, you need to proving if you have f of x is x with the power of n, you need to prove this. You need to prove, okay? Prove this. But before we are going to prove, I will share with you a little bit about differentiability, okay? And then we can go to the power rule and then several rules in derivatives, okay? It's really basic. I think you're already familiar, but let's get review and maybe you have more understanding in derivatives, okay? So first, I will share differentiability. So let's just write f prime, let's just say c, our number. As our limit definitions, we can write our limit as this form. Okay. The differentiability start with if the function is differentiable. at x equals c. Then f is continuous at x equals c. That's the first one. The second one, if f, the function, is not continuous at x equals c, then function is not differentiable. So the function is differentiable if the function is continuous. So you need to check the continuity. The first thing is to check the continuity. So how to check the continuity? You can use limit. Okay? You can use the limit x approaching a from the left side. It needs to have the same value if you approach from the right side. And then you can conclude this is same. And this is also the same as f of a. That means it's continuous. So every hole, every jump, every discontinuity, it will render discontinuous. Okay? So you need to have smooth, and every point is there in function. Okay? There will be no hole. That's continuous. Okay. I will give you some example, quick example for differentiability. So what you need to remember is, I think, just these three graphs. Okay, if you have this graph, um, and then okay, there are three graphs here. Okay, the first one, we have a corner here. The f, the function has a corner, so which means this is not differentiable. Okay, I will write later. Here we have discontinuity, or jump discontinuity, you can say. And in this, the third one, we have the vertical tangent. In this red line is having vertical tangent. Okay, all these three is not differentiable. Okay, so all these three f uh, fail to be differentiable. Okay, I think this three is enough to represent the not differentiable. Corner, discontinuity, and then the vertical tangent. Okay, any questions so far? Okay, good. Okay, so Remember this corner, discontinuity, vertical tangent. Easy, right? Just that. Mm, okay. So I will directly go to the power rule. So this is when you have the functions and you have the derivative, right? Okay. So let's start with the, yeah, let's start just writing the h approaching 0, and then start with the definition by limit. So maybe in your textbook or maybe in the exercise, you will see some chapters or some problems saying that calculate derivatives by definition, by limit definition, which means these definitions. Okay. This is called the limit definition of derivative. Okay, okay, from here, uh, this is our functions, x with the power of n. So we using this x with the power of n to our limit. Okay, so it will be limit sh approaching 0. So it will be x plus h, okay, with the power of n minus x with the power of n, and then h, right? Okay. Any idea what we should do? Any idea how we should solve this? If we have squared, we can just expand, right? If we have, how about if we have 3? We can also expand, maybe 4, 5, more, right? It will be more and more longer expansion, right? If we try to expand. But let's see, okay? Let's see if you remember. If you have a squared minus b squared, you will have this, right? Usually in exam or any test that have an algebra, this form sometimes helps a lot, right? If I have cube, what will be here? A minus b. And about here, what about here? What will happen? A squared, right? A squared, and then ab, right? Yeah, this is also sometimes you see in some exam, okay? Because I remember, I think in high school, I also remember how to expand this form. How about 4? Before it's squared, but let's just guess. This should be cube, right? Should be cube, right? How about the next one? A or a squared, you can use both. So a squared b plus ab squared, right? Because that's the only possibility. Okay. So if you see here, okay, this is interesting actually. This is 1, 1, 2, 2, right? This is 3, 3. Okay. And because 2 is here, like for example, the the red color here, the middle part is only 1 and 1, right? Let's see the cube here. We have cube here and cube here. Because it's 3, we have 2, 1, 1, 2, right? For A and B, the combinations, okay? The patterns, okay? So we have this is 2 and this is 1, this is 2 and this is 1, right? for A and B. So for fourth, we'll have 3, right? At least. So I will just directly go to the conclusion. If we have A to the n and B to the n. Okay. Every time we are doing the examples above, the first one here, A, should be less than 1, right? So n minus 1. Okay. And then plus. Okay. The next one should be minus 1, right? The A and minus 2. Okay. But there's B up here. Okay. Let's just imagine, okay, there are a lot of going on, like maybe 3, 4. Okay. So let's just dot 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 and go for the last two parts. Okay. Because the middle part, it's you can get a lot of number there. Okay. Okay. Plus. So here we start with A. The before is only B, right? So you start with A and then we make B and n minus 2. Okay. And plus B and minus 1. At least you have now this expansion for A with the power of n and B with the power of n. Okay. Okay, this is precisely A and B n, right? So we can use the same way to solve this. Okay. So we can factorize the x plus h minus x going outside and then make the form similar to our conclusion here. Okay. I'm not sure in high school, do you get like proving the derivative or not? No, right? Okay. Yeah, I also get it in the university. I just get it the derivative in high school. Oh, just x squared, oh, the 2 going down, or it's minus 1, okay. And then, oh, simple, easy. Okay. Okay, let me write in the next page. So let me, okay. So let's factorize x plus h minus x, like a mean minus b, right? Oh, don't forget there is a limit here. Oh, maybe there will be really, really long, so I will just write all here first. So the first is, so this is A, this is B, so we write x plus h and minus 1, right? And then plus x plus h and minus 2, and then x, right? Plus, I will going down here, plus just x plus h, and then x and minus 2, and then plus the last one is x and minus 1, and then close the bracket. And this all should be divided by h. This x minus x, we just can cancel that. And we are still having h here. But because it's already outside, we can cancel this h to this one. Okay. So the rest is just the bracket form here. Okay, let's see here. According to our limit, as h is approaching 0, because the h at the bottom, we already removed that. We can input our 0. Okay, so this 0, 0, 0, right? In all h. Okay, we put inside. So the first one is becoming x with the power of n minus 1. Okay, and then see here. Okay, this is 0. The h is 0. So x n minus 2 multiplied by x. So you will change minus 2 plus 1, right? Okay. Okay. So dot dot dot, and then we have the last two parts is x n minus 2. Same. x n minus 2 n minus 1, right? And the last part is just x n minus 1. So all will be x n minus 1, right? How many of x n minus 1 here? Let's say it's n times, right? Okay. So we can simplify our plus 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 here become n and multiply by x n minus 1. Okay. So the proof that if you have f of x, so your f prime is okay. So you can maybe, if you want to show off to your high schoolers, junior, I can prove you. Or you can ask them, how can you know that this, and then you can show them, oh, here it is. Maybe if you want, if you want. Because when I was in high school, I went to like a tutor, right? Because I want to get my grade perfect, right? And then the tutors, I was impressed by the tutors because he can explain and then like giving a proof. And then later I realized when I entered university, oh, this is where it comes from. Okay, so so this is called the power rule. Okay, power rule. There are another way to prove this, but it requires another tools. But I will show you later after we deal with another tools. Okay, any questions before we continue? Or do you want to have break? No, or just continue? We can have like 5 minutes break if you want. Let's have break. Okay, 5 minutes break.
There is the H 6H is 3H 3.
Oh yeah, three. Yeah, should be three.
And it is because of H approach zero, so
So
this
zero, yeah, zero.
cancel.
Yeah, zero. Yeah.
I see
This one?
now.
Before this or which one? This or which? This?
I lost.
Here? Oh, yeah, yeah.
No, no, no. At least.
Oh, this. Okay. Actually, it's oh, here. Yeah, yeah. Okay. Maybe I will upload after like every chapter finish, so you can like focus on in which chapter.
So you will upload this.
Yeah.
Thank you.
Okay, for online students, we are having a breaks for a few minutes. So maybe if you have questions, and also I want to make sure that you already have arrived in Taiwan, right? Most of you. Who's still outside Taiwan? Also flying on the okay. So when you will come? 5, okay, 9, 5, 11, okay, 8, okay. Okay, so we will have a quiz in the mid of October. Okay. We will have a quiz in the mid of October, but because you are still either outside of Taiwan or still in quarantine, we will have the quiz. I will send the file to you later, and then you just need to fill in the answers, and then you can scan or photos and then send back to me. I will announce the procedure later. Okay. Our quiz will be in the mid of October, maybe 13 or 15. I will announce this week in the Moodle. Uh, check the Moodle this week. Okay, the QR code. Okay, let's continue. Continue. Uh, uh, okay, some rules for derivative. Um, I think this is also not too complicated. So if you have a constant c, so c is constant. So, oh, by the way, usually if you see any d over dx, it means this is derivative. Okay, this is derivative. So derivative of, so this is the function. So usually it's dy dx, but you can change y to any functions, right? So you can also write df of x dx, or you can write d dx, and this is your function here. It's also becoming a tool. So this is d over dx is your tool to derive. If you want to write in the math notations. And if you have d dx, let's say this is uh, fg, all function is already defined and continuous, okay? And you have plus and also minus, okay, plus or minus, okay, because it will be the same rule. You can separate these two functions. Uh, Calculus, derivatives, integral, etc., or math in general. Um, Actually, it will be helpful if you maybe in the future you will need to get in touch more with any software that includes visuals like MATLAB or mm, yeah, or any software that's similar to MATLAB, because you will understand the, because you already know the basic. When you apply to some modeling, uh, it will be much easier. Okay. Okay. Yeah, this is the basic derivative rule. And there are another rules. Okay, maybe I can show you one or two and proving some of that rule. Okay. Remember the product rule. Okay, so you have functions of f of x, g of x. What is the derivative of f g? You remember? So f prime x gx, right? And then what? Plus, right? Plus. I think it's also appear a lot in high school exam. This part, right? Just checking, because I just realized several news from Taiwan. related to math problems in elementary school. For example, okay, for example, I think you've heard the news. This is for for, for elementary 9 years old student in the test in Taiwan. In Taiwan, yeah, I've read the news and it says it's from Taiwan. This is just for your information. Uh, you can try. I solve it maybe around 10 minutes. 15 minutes. 15 minutes. 15 minutes. 10 to 15. Because you need to at least you need to try some numbers that make sense first, and then make it into the calculations, and you get it. This is just intermezzo. If you want to try, you can try. But let's back to our topic. Okay, let's back to our topic. Oh yeah, if you want to solve, you need to solve this first. And it's become E. That's the first one. And if you get it, maybe some possible number, you can try all and get the A, B, C, D, E. Yeah. I don't know why the teachers give the student this kind of question. Okay. So the first one is the product rule. Okay, the second one is the quotient rule. I will later give you some notes about product rule and quotient rule. Quotient rule means the f of x divided by g of x. So similar to our product rule, but the difference is this is minus and get all the way down. And then at the bottom, it's g squared. Okay, in the next page, I will try to explain the product rule first and then quotient rule if we have time, but maybe just product rule. Okay, so the next page, mm, let me write let hx is f of x and g of x like that. And then your h prime x is equal limit h. Let's start from the definition of limit. Okay, so I will start with the h is equal f multiplied by g. And then because h is fg, I will change all the h here. Wait, let's not make h because it will be confusing with h with the limit. Okay, let's try to another form. It will be confusing, if we use h. Hmm. Let's just use F, big F like that. Okay. Let's change the big F into small ng, and then F. Okay. And then divide all by H. Okay. And what will happen? Okay. Uh, this is a little bit trickier than before. From before, we are solving through a pattern in exponential in the polynomial functions, right? Here, okay, at the top, we add and subtract, okay? Fx plus h and gx. So it will be limit h to 0. So I will add with different color, add this x plus h dx. Mm, and then minus f the same expression. So plus minus, it should be okay, right? To add and subtract the same expression, it should be okay, right? But why we need to add and subtract? Well, you will see later. And then the last part is f of x, g of x, okay. And all divided by 8. Okay, now you have some expression here. This is having 1, 2, 3, 4, 4 expression. Okay. Now, grouping. Grouping the fx plus h and g of x. Let me write. Okay. So I will group the fx plus h. Or let me write the bracket for you. Do the bracket. And plus, okay, gx Okay. Now we have this all this grouping. Okay. So we add and sub fx plus h and gx here. We add and subtract. So it's becoming this 2 and 3 expression. Okay. And now we are grouping the fx plus h and g of x. Okay. So first from here and this 1 and 3 grouping, and then 2 and 4. Okay. So it become g, in the middle it will become gx plus h minus g of x, and at the last one is fx plus h minus f of x. Okay, and all divided by h. But I separate the h. It's the same as all separate, but I want to make sure that you get my idea here. If you see here, this is limit h to 0, right? Of x plus h. I can make the limit separate. So all of this is limit h0. This also limit as h0. This is also limit as h0. Okay. Remember our definition of limit. Okay. Here is the definitions. Okay. If we have f prime as our derivative, the definition is here, right? See this form, the limit form here, x plus h minus f of x over h, right? And see this form, and see this form. Okay. So based on our definition, this become just f of x. You plug in 0 here. Okay. Multiply by g prime x plus gx f prime x. Okay. Get it? But it is a little bit tricky because of this adding and subtracting fx plus h and gx. But to make sense of all this process is how we can make sure that from uh, our form here, we can actually rewrite the form to make this form appear one more time. So we can make sure that that one is the derivative. So this just f, this one is becoming g prime, right? This is just g, and this last part become f prime. Okay. Okay, basically, the product rule and quotient rule, the proof is similar. Adding, subtracting, the same thing, but the difference is product rule fg, quotient rule is f over g. I think if you want to prove it by yourself, I think you can do it. The same similar process, but I will show you later. Okay. Okay. Next page, I will go directly to quotient rule. Let's just use the same f, the big F. Okay. This is f of x divided by g of x. Based on our definition, this is x plus h Uh, let's rewrite all in f over g. Okay. Let's solve this rational. Just simplify all g going down. So let's just write h g x plus h g of x. So the rest will be, this is gx f x plus h minus is correct, right? Yeah. Okay. Now add and sub. The difference is we add and sub fx and gx. So let me write f first. Fx plus h dx. Okay. And to get to y it is using fx dx, let me subtract first and add. Okay. Let me subtract first and then add. Same plus minus and then add. Okay. And then the rest will be minus f of x dx plus h. Uh, we have h dx plus h. Yeah, that g will be squared, right? You can see it in the form. Okay, next, grouping gx and f of x. Okay. Okay. And I still have some works, but I think we will continue next Thursday. Is that okay? Okay. Okay. But let's just continue Thursday. Okay. Okay, we will continue the class next Thursday. Okay.